about integrating AI services within a FHIR resource event stream to extract hidden data. The next session has been pre-recorded. So first we are going to show you the presentation, and afterwards you will have the chance to ask your questions directly to Scott. So please feel free to ask any questions in the Woover Q&A chat box, and we'll be constantly monitoring that section and we'll get back to you as quickly as possible. And with that, I would say we get started.
Hello, and welcome to my tutorial. Today, I'm going to show you how to integrate AI services within a FHIR resource event stream to extract hidden data. My name is Scott Carrier, and I am a senior software engineer at IBM Watson Health. I work on an open source project called Linux for Health. Linux for Health is a project we're building out to facilitate healthcare data connectivity and edge of network processing. And that is an Apache 2.0 licensed open source project. I also work on IBM Watson's Annotator for Clinical Data, or ACD. ACD is a healthcare-centric NLP service available in IBM Cloud. I have about 10 years of experience in the AI healthcare domain, and I'm a recognized IBM Master Inventor with 56 patents granted and several more pending. In today's tutorial, I'm going to show you how to consume FHIR resources from an event stream. I'm going to show you how and where to extract unstructured text within those FHIR resources. I'll show you how to use a pre-trained NLP service to analyze that data. I'll show you how to publish the NLP output back to an event stream. And I'll give you some ideas on how to leverage that output to create value-added outcomes for your organization. This is a high-level diagram of today's tutorial. Over here on our left, we have the repository, our FHIR resource repository. And for that, I'm using Apache Kafka. Kafka is an open source streaming platform. And you can actually use the Linux for Health application to publish FHIR resources to an event stream such as Kafka. Over here in the middle, I have our data orchestration component. And for that, I'll be using Apache Camel, which is an open source integration framework. And Camel offers a wide variety of components or add-ons that make this type of orchestration much easier. And they include support for a wide variety of different data formats, including FHIR and HL7. Over here on our right, we have the AI analysis component. And the category of AI I'm using today will be natural language processing, or NLP. And for that, I'll be using a pre-trained managed NLP service. And I've listed a few of the services that are available for healthcare NLP up here. In my code examples, I'll be referencing ACD, which is the service I work on. But since the integration is over HTTP request, it's fairly simple to swap out different NLP services. So I'll show you how to do that. Okay. What you're looking at here is a demo application we provide with ACD. And the reason I'm showing it is for those of you who may be less familiar with natural language processing or what kind of information you get back from an NLP service. So with NLP, as you might imagine, you're sending unstructured data to a service. That service is going to analyze that data, looking for the concepts that it was trained to look for, and it returns its findings in the form of metadata we call annotations. And that's what you see graphically depicted over here, these annotations over text. If you were to hover over an annotation in the demo app, you'll see that there's additional metadata provided for each one of those annotations. And over on the right-hand side, you see the inventory of the types, the the concepts that were found in your text, as well as the instance count. So you can see here that there were 8 instances or mentions of diagnoses. There were 2 mentions of lab values, etc. Okay, so I just wanted to leave you all with a graphical image of what you're getting back from an NLP service. Okay, so where are we getting our unstructured data from within FHIR resources? For today's tutorial, I'm focused on 2 sources of unstructured data. The first are these base64 encoded attachments, these inline attachments, such as what you see here. And you'll find these within resources such as document reference and diagnostic reports. The second source of text comes from these narratives. These are XHTML elements you'll find in a variety of different FHIR resources. And they look like what you see here. There's an example right here. Okay, so those are the 2 sources I'm going to be processing. For those of you who may not be familiar with Kafka or what those topics and messages look like, this is a sample message that we're going to be consuming from Kafka and processing with our data orchestration code. This is a sample taken from a FHIR resource that's been published to Kafka using the Linux for Health application. And there's 2 main components to it. Up here, you have a variety of metadata. This kind of talks about what the type is, what the data format, the different routes, timestamp, etc. And down here is where we have our base64 encoded FHIR resource. So much like the inline attachments, we encode FHIR resources in a data element. Okay, so this is the input of the data orchestration code that I'm about to show you.
Is it possible to remove that black square in the top?
So as I mentioned, I'm using Apache Camel for data orchestration. And what you're looking at, the code you're looking at here is what's called a route. And the orchestration will be performed using a sequence of these routes. Within a route, there's a notion of endpoints, and they can be consumer endpoints like what you see in the from declaration. In other words, you're defining where the input to the route is going to come from. And then you have producer endpoints, which are these to declarations. So that's where you're sending data to. The object that flows through these routes is called an exchange message. And so that's the data. You can set properties and headers on the message as well as the message body. So that's just a really high level description of what Camel is and what these routes, how these routes perform. So if you're not familiar with Camel, that's okay, because I've annotated these slides pretty heavily. So you'll at least get to follow along. But I think the coding is pretty simple enough that you should be able to kind of look at it and at least get a sense of what's happening. All right, so this is our first route, our sort of the starting point to our data orchestration. So as I mentioned, Apache Camel offers a variety of different components, and the endpoints that you define, the consumers and the producers, are in a URI format. So that beginning part of the URI is how you reference some of those components, such as this Kafka consumer component here. And each component has its own documentation, so you can look at and understand how to use these components. But I'll be using the Kafka component to consume a set of topics from our Kafka server. So the way you designate that is a comma-separated list of topics, like you see here. So we have document ref, we have diagnostic report, and we have our bundles. And then you can also define the brokers that you're using. And for this route, so this route is responsible for consuming topic messages from our stream, or Kafka. The input is going to be a Linux for Health message, like I showed you in the previous chart. And the output is going to be a FHIR resource. Okay, so here we're consuming those messages off Kafka. where you see these choice stanzas, that is conditional logic. So you see these when clauses. So what we're doing here is we're checking to make sure that that message is a FHIR R4 resource, because that's just what we expect to process. So you may recall the FHIR resource itself was base 64 encoded within that data string. So here we're extracting that data string and we're decoding it. So what we have right here, once we get to that point, is our FHIR resource, which is a JSON representation. I'm extracting the resource type. And the reason I'm doing that is so I have conditional logic here that checks to see whether it's a bundle or not. So if it's a bundle, the way I've constructed these routes is that the next route in the sequence is going to expect a FHIR resource. And a bundle is a FHIR resource, but it's expecting an individual FHIR resource. And so what we're doing with this split call right here is we're just breaking out all the individual resources within the bundle. And we're going to send that to the next route we're going to talk about, which is our FHIR resource. And if it's not a bundle, it just sends it off to the FHIR resource anyway. And direct is also a Camel component, but it's a component that basically declares a synchronous invocation of what is typically another route. So I have, you'll notice this direct FHIR resource in the from clause of the next route that you're going to see. So that's the consumer. This is the producer endpoint. So this is sending those FHIR resources off to that next route. So our FHIR resource route is responsible for processing the individual FHIR resources. The input is a FHIR resource, the output's a FHIR resource, but it's a FHIR resource that's going to be routed to the appropriate subroute. Here with these set properties, I'm extracting some data points regarding the FHIR resource, things like the type, the subject reference, and the ID. And I'll talk a little bit more about that later, but I'm grabbing that information so I can eventually have traceability from my NLP output back to that FHIR resource. And again, I'll talk a little bit more about that later. So down here, we have another conditional set of conditionals. So if it's a document reference or a diagnostic report, I'm going to do some special handling there. And the reason being is that those two resources can contain attachments, but they can also contain narratives. So if it's one of those resources, I'm going to multicast or copy that exchange message. And in parallel, I'm going to send it to two different routes. My TextDiv route, and I have a resource-specific attachment route for docref and diagnostic report. And I'll show you those routes and you'll kind of see why. So if it's those two, send it off in parallel, copy that object, and in parallel send it to two different routes. If it's not one of those types, meaning it's some other resource within the bundle, then just send it off to just the narrative route. So this is that TextDiv route. It's responsible for extracting text from FHIR resource narratives. Its input is going to be a FHIR resource. The output is going to be unstructured text that's NLP ready for processing. So within this route, we have a simple conditional here. We're just checking to see if a TextDiv element exists. And you can see that example of a narrative. So we're just going to see, does this element exist? If it does, what we're going to do is extract that string. And we're going to use our next Camel component here called Tika, Apache Tika. And Tika is a really cool utility that can translate or extract text from a variety of different formats, whether it be like a PDF, Word document, HTML. It can just process or convert just a wider variety of different formatted content to text, which is what we need to do proper NLP processing. And I'll show an example of that here, how we clean up this dev string. So once we do that, once we pass it through Tika, we now have unstructured data that's ready for NLP. So in just 3 simple short routes, we've gone from consuming messages off Kafka to having unstructured text that is now ready to be processed with NLP. And you can see how simple that line of code there, that Tika line of code is. Just one little line of code does a lot. So let's look at that. So over here on the left, you see what those narratives look like in FHIR before we pass it through Tika. So this is what it looks like before, and this over here on the right is what it looks like after. So you notice that Tika not only strips out all those tags, but it maintains some level of formatting that was inherent in those tags. And there's a couple of reasons why you want to send this text over here on the right to an NLP service versus this text on the left. So one reason is all those angle brackets and tag characters, NLP parsers will sometimes have a hard time parsing that out. So there's a process in NLP parsing called tokenization. And what that's doing is that's identifying all the tokens or words, assigning parts of speech, identifying sentence boundaries, things of that nature, sort of foundational NLP processing that oftentimes downstream NLP annotators use to find the concepts that they're trained to find. So all those angle brackets and characters can lead you to what's considered like a suboptimal parse. And like I said, if you get a suboptimal parse, that impedes downstream annotators from finding what they need to find. The other consideration is that when you're using an NLP managed service, oftentimes you're being charged by the amount of content that you're analyzing. And so by leaving in all these angle brackets and tags, you're not going to find anything useful over them, but you're adding to the volume of content that you're being billed for analyzing. So it's recommended to clean it up like this. And you can see how easy it is to clean it up in Apache Camel with that Tika component. Okay. So now we're back to processing attachments. And these are those 2 resource-specific routes I had. And the reason being is just the attachments exist in different JSON paths. So in diagnostic report, it's in presented form. In document ref, it's in the, there can be multiple attachments within document reference. And so this is taking all of them and passing them on to the direct attachment route, which both of these routes funnel the attachments into. So let's look at that route. So this route is responsible for extracting text from FHIR resource attachments. So much like that narrative route we looked at, where it was responsible for processing narratives, this is basically the attachment equivalent of that. So one thing we're going to capture up front is the content type. And you're going to want to pay attention to that because in FHIR, there's pretty broad support for different MIME types within these attachments. So it's going to be important to know whether you're dealing with like a PDF document or a Word document, plain text, HTML. That's going to be pretty important to know what the content is, so you can make sure that you extract the text appropriately for NLP processing. The other consideration that is not shown in the code here, and I should mention that all the code you're seeing is primarily for demonstration purposes. This is not hardened production-ready code by any stretch. It's just for demonstration. So you don't see this here, but the other consideration is the language. So different NLP services will have varying support for different languages. And so if you extract something like an attachment in Spanish, French, or German, check the NLP service to make sure to see whether it can handle those languages. And so you don't want to send off a document to an NLP service that it can't process correctly. So what we're doing here with like we've seen before, we're extracting this base64 encoded string. We're decoding it, which gives us our attachment. In our conditional here, we're checking in this example just for PDF or HTML. And if an attachment is PDF or HTML, we're routing it through Tika, like we did with the narratives. And it's actually the exact same call to Tika. And so that's gonna, if it's a PDF or it's an HTML, we're gonna have our clean text that an NLP service can process appropriately. And then if it's text plain, we assume it's NLP ready. So let's have a look at an example. So as I mentioned, you want to pay attention to content type and language too. And so if you processed an attachment and just did the base64 decoding of it, this is what you have over here on the left. So again, you don't want to send that. You don't want to send this to an NLP service. When you pass it through Tika, you get the nice clean text over here on the right. One quick note about this text right here is that we consider this is text that's considered to be semi-structured, in part because it has these columns, this notion of a column right here, 4 columns. And a human looking at that can instantly detect that those are columns and that this is the header. So, oh, okay, these are the tests, these are the units, these are the values, these are the reference ranges. Humans are great at looking at that and instantly recognizing that. NLP services will vary in their ability to process this type of data. So my recommendation is if you have unstructured data, do some evaluation with the service that you intend to use to make sure that it can detect what you need it to detect. Okay. So we've processed our narratives, we've processed our attachments, and we now are at a place with our routes that we have plain text in both cases that's ready for NLP processing. So this route here is responsible for taking that text, sending it off to an NLP service, and posting the analysis response back to our event stream. Okay, so what we're gonna do with the actual request, and our integration point is REST APIs or HTTP calls. So what we can do here, and it looks, if you just look at it, it looks like a regular endpoint. What we're actually using is the HTTPS component of Camel. And what that means is, if you look at the first 3 lines, that is in fact the endpoint you would use in something like a curl command or a postman call to ACD. Those last 3 properties you see, the auth method, username, and password, those are properties for that HTTPS Camel component. In other words, these are not getting passed as is to ACD. Rather, they're instructing this component to make this request you see right here. So it's just something to understand about how Camel works. And so as I mentioned, this request right here is what an ACD request looks like. If you are using a different service, it's just a matter of using a different endpoint. So that's one nice thing about using a managed REST API service, is that the integration is primarily through an endpoint. So it's pretty straightforward. Now, what you want to do here, if you're using this component, is you're going to want to define the HTTP verb. In this case, it's a post call for ACD. And for ACD, you're going to want to set the header, the content type. So in this case, we're sending plain text to ACD. So our content type is text plain. And so the HTTPS component will use this verb right here and will propagate the content type to ACD. The response you get back at this point in the route, the response from your NLP service will be the exchange message object body. And the return code will be populated in this header right here. so Camel HTTP response code. So here I'm just doing a check to make sure it's 200 or successful. And in this part of the code, what I'm doing is I'm going to take that response and I'm going to populate a what we call a message envelope, which is just a plain old Java object or POJO or Java bean. And so like the cases we saw previously, I'm going to set a data property to the base64 encoded representation of my NLP service output. And what I'm going to do beyond that is I'm going to capture some metadata concerning the FHIR resource from which I got the unstructured text with which I used for NLP analysis. And the reason being is I want to, when I post that NLP response back to my event stream, I want to make sure I can trace it back to the FHIR resource from which the text came from. And I'm going to do the same thing about the NLP service itself. So I'm capturing a couple of data points like the service name. In the case of ACD, I'm capturing what we call our annotator flow, which basically just designates which annotators and which configurations are being used. You want to catch the version. You want to capture meaningful metadata concerning both FHIR resources and the NLP service so that you have that and maintain that traceability once you post that NLP output to Kafka. It's really important. So once we populate that POJO and we set that to be the body here, we're going to convert that POJO to JSON. And that's what we're going to publish back to Kafka under this NLP_output topic. And here's an example of what that looks like. Okay. So now that we have our NLP output in Kafka, what can we do with it? How can we take that output and create some value-added outcomes? And here are a couple ideas for consideration. The first of which is to use that output to augment your structured data in FHIR. And there's kind of two parts to that. So say you had a structured resource defined in FHIR, your repository, say it's a medication. And it's possible that the NLP service will detect mentions of that medication within one or more clinic notes. So one thing you can do is try to link those mentions in the unstructured data to your structured resources in FHIR. And that helps you with this question right here. So what are physicians saying about a particular resource and when did they say it? So you can see the resources as they exist in FHIR, but in many cases it'd be helpful to look at what physicians are saying about it. If it's a patient's resource, what are they saying? What's the discussion regarding a particular medication or some other resource? So another part here is that it's possible that the NLP service will detect concepts in your clinical data that are not yet defined as resources in FHIR. So your NLP output can serve as a way or a method of creating new FHIR resources. If you go that route, much like the traceability we made sure we had when we published NLP output to Kafka, you want to collect similar metadata or include that same metadata in that FHIR resource so that when you're looking at the resource, you know, A, it came from NLP, it was discovered through NLP, which NLP service, which clinical notes can I refer to, and that becomes your evidence. So if it's ever in question, where did this resource come from? You know exactly where it came from. It's really important that you maintain that. And that's in part why I suggest you capture all that information up front. You don't want to, when you publish it to Kafka, you don't want to have to redo all your processing because you forgot to collect all that information that you need to create value-added outcomes from that data. And the other application that you can create is something referred to as a semantic search or a highlight over a body of text, such as an LPR. So in other words, instead of dealing with straight raw text, you're going through the text or navigating or searching the text by way of all those annotations. So it just gives you some structure to more easily navigate a body of text. And I included a blog link below that gave you the blueprint for how to construct such an application. And that concludes today's tutorial. Here's my contact information, and I'll open it up for Q&A now.
Thank you so much, Scott, for that presentation. And with that, we're now switching over to the Q&A section. We have plenty of time for questions. So if you have any questions, just drop them into the Q&A chat box in Hoover. First question that I see here is, do you have a recommendation for an annotation format to prefer for this kind of NLP annotation in free text patient/consultation information?
I'm sorry, a format? Could you read that again?
Do you have a recommendation for an annotation format?
Annotation format. In what sense? In the response or the input? If whoever answered or posed that question could elaborate.
It's in the response I'm interested in, Scott. Hi.
Oh, hey, yeah, that'll vary based on the service that you're using. And so there isn't a standard format that I'm aware of that the services that I listed in the deck will support. So unfortunately, every service is going to return slightly different JSON that you have to respond to. But typically in the services I've seen, they are like in the JSON response, there'll be a set of, there'll be like an array of the different concepts. So you should be able to go to a response and pull out like all the medications or all the conditions and things of that nature. So some of the better services will at least group the different concepts that they return, but the JSON will vary by service.
Thank you.
Sure.
Okay, so our next question is about how to store the original information with the extracted NLP. How to model the certainty of the extracted data for future use.
Yeah, that's a great question. And unfortunately, I didn't have too much time to go into that in the deck or the tutorial. But if you look at, I did provide a link to a good Amazon blog that shows you how to store that data for the purposes of doing some type of indexing for a semantic search. So typically they store that the text as well as the annotation output in a database, such as like MongoDB, and they'll index the annotations in a service like Elasticsearch. And that will allow you to do a semantic search over the text. So you're able to do searches based on the annotations that map back to the text and the documents. So there is a link in the deck to, like I said, a good Amazon tutorial that gives you basically the blueprints for how to build that.
Would that be the same strategy as for the metadata that you extract from the file resources, or do you store that somehow differently?
You could store that the metadata from FHIR resources if you wanted to. You certainly could store that along with the annotations. So you could search by both the NLP output as well as some of the structured FHIR attributes. That would certainly work. That's an interesting idea.
But there aren't any, let's say, standard extensions yet that you just insert into your FHIR resource where you can put that metadata.
Yeah, not that I'm aware of. I've done, that might be an interesting talk for a follow-on conference, but we typically had like key value pair extensions to FHIR. So we'd store like the processing date, the service we used, different types of metadata. So again, we could track back when you had a FHIR resource, we know where it came from, which text was sourced and things of that nature. But nothing, just mostly key value pairs in FHIR extensions.
Okay, so we have one more question about how to capture the logic or rules that were used when running the NLP algorithm, so we can trace on how we got to the output.
That's tricky because typically when you're using a pre-trained service, typically all of that is in the back end. It's more of a black box. And so that's really hard. And a lot of these services are continuously deployed and updated. And so it's very hard and impossible in some cases to track back to what was the version of the machine model that was used to produce some set of outputs. But that is an interesting conundrum because it would be good to have that traceability. But that's kind of the trade-off, I guess, of a managed service, is that it's updated continuously. So you get the benefits of improvements and refinements over time. But one downside might be that traceability back to the specific version of the model that that service happened to be running. But one way to combat that would be to use a pre-trained model that you have more control of. So it's not a managed service that way. So in other words, you run it locally. But then the trade-off there is you have to run it locally and you can't use a managed service. But I would say if that traceability is important, you might want to run your own model. And there are pre-trained models you can get out there that you can run yourself. And that way you have full control over which version of the model that you use. But it's kind of that trade-off, managed service versus a model that you have to run and host yourself. So it depends on your needs.
Can you speak a bit about the quality issues that you're seeing in real life? So do you have a lot of failures to extract the data, or is the quality relatively high?
It's yeah, I mean, it depends on the data itself. You know, in the healthcare space, there's a lot of OCR text. And so OCR can cause a whole host of challenges. ACD, I can speak for ACD. We offer a spell checker annotator. So if you have OCR issues such as like I's becoming ones or commas becoming periods, little things like that can trip up your NLP annotators, we offer a spell checker annotator that can make those corrections on the fly, so that as you send in the OCR text, it'll make those corrections, which gives the annotators a better shot at detecting what they are trained to detect. And you have that full traceability. So you know in the response what corrections were applied to the text. And we have some really nice deep learning models that do a really cool job of getting it right. We don't always get it right, but you at least have that traceability in the response. But yeah, NLP in general is really hard. You know, it depends on the data that you're trying to extract. Depends even on the department within your hospital. If you're working in a hospital, it depends. Each department has different ways of making notations. And, you know, since we're talking healthcare, it's really important that you have a good degree of accuracy. But it's a challenge for sure. It depends on what you're extracting. If it's something simple, I mean, medications, you can pull it out, but then what does it mean to your solution to detect the medication? Are you trying to figure out which medications a patient is taking and their start and stop times? It depends on what you're trying to get from the data, how you intend to use the data, and that tends to drive the need for accuracy. How accurate does it need to be? Or are you looking at more for navigation? If you're looking at it for more navigation, so here's all the concepts or mentions I detected in the text. Nobody's saying the patient has these conditions or these medications. It's just for navigation purposes. That tends to require a little bit less accuracy, or I should say you can tolerate less accuracy. But if you're trying to ascribe conditions or medications to a patient, that typically requires some level of higher accuracy, or at least triangulation. So we have these mentions in the text, and we can triangulate that with like their medication orders. So we can somewhat confidently say that the patient is taking some medication, but it's tricky. It depends on what you're looking to do with the data and the data that you're looking to extract from the text. But it's certainly hard. It's not easy.
Related to the question of OCR, do you see more issues related to text generated by voice as compared to text generated by OCR?
That's a good question. It depends. I haven't actually done a lot with transcriptions personally, so I haven't waded through a lot of that data. I guess both would be, with transcriptions, I imagine anyway that you'd at least get sensible words. It might be the wrong word. But with OCR, the trick there is you just get some really crazy characters that just don't make sense. It's not even a word. It's just because it's doing the optical kind of character by character. So it's not always piecing together like, is this a word that I produced? And sometimes if you have like something that was faxed, it'll be faxed 5 different times. So it's not even the first fax. You're getting 5 faxes of the same fax later. So you have like shadows and the text is crooked. So OCR does pose certainly some challenges. The technology is getting better. You know, more ensemble models are being employed on the OCR text to come up with sensible words. And like I said, we have that spell check annotator to help map a word that's not correct to the closest matching vocabulary. So we're technology to handle it is getting better, but it remains a problem or a challenge, I should say.
We have time for one more question. So let's end this by maybe talking a bit about the pipeline on how the FHIR data gets to the event stream. What is your architecture like?
Yeah, I'm using the Linux for Health application. That's an open source project. Anybody can go and download or contribute to it. And in that application, you put as a REST-based API that you post a FHIR resource to it, and that will be posted in turn to our Kafka event stream. And all of the different resources are posted to different topics that you can subscribe from. And from there, there's a NATS server that can do notifications of these resources. And so how it gets to Kafka could vary quite significantly. I think even FHIR servers can post to Kafka, or they can populate a Kafka server or a data lake. And so it can vary wildly how they get there. In my particular case with the code I showed, I'm using the Linux for Health application to do that.
Okay, thank you so much for your presentation and this Q&A section. If you have any more questions, simply post them here in the Q&A box. And I hope you enjoyed this presentation. Thank you so much.
Thank you, everyone. Appreciate it.
Thank you, Scott.